Hello, this is Robert Davies with the Utah Climate Center. In this episode of Utah Climate Notes, it's time to talk about global warming. We began this series by defining the notions of climate and climate change and asserting that significant climate change is underway. Now we begin to look at the details of this assertion, and we'll begin with the question of warming. Driving Earth's ongoing climate change is an overall warming, a global warming, of the Earth system, its oceans, land, and atmosphere. And this is what global warming looks like, from the end of the 19th century to the middle of the 20th to today. As you watch the colors on this graphic change, from the cooler blues to the warmer reds, you're watching the progress of warming across different locations. The warmer the color, the more the change. Well, let's watch it again. From the end of the 19th century to the middle of the 20th to today. Now, there's a great deal of nuance in this data, to be sure, but two things jump out immediately. First, it's clear that the entire planet is warming, and second, this warming is not uniform. In particular, we see the higher latitudes in the northern hemisphere, the Arctic regions, have warmed considerably more than the rest of the planet. And at this point, I'd like to stress once again that this graphic depicts temperature change, not absolute temperature. The Arctic has not become warmer than the tropics, but it has warmed more. If we average the amount of change across all locations, we find the planet as a whole has warmed just over 1 degree Celsius over the past century or so, which is about 1.8 degrees Fahrenheit. And for future reference, you can always convert to a Fahrenheit change by roughly doubling a Celsius change. And this can be useful since climate scientists tend to report temperature data in degrees Celsius. Now, the nice thing about rich data sets is that we can look at them in different ways. Here, we've plotted this same temperature data not spatially, but as a time series, a single global average temperature change for each year going back 130 years or so. And at this point, a quick note about temperature change or anomaly. Climate scientists speak in temperature anomalies rather than absolute temperatures simply because it's more convenient. In the same way, it's more convenient to talk about the height of a door frame above the floor instead of above sea level. Well, in this case, the temperature floor or reference level has been defined as the mid-20th century average, and the vertical scale is temperature change or anomaly from this reference level. As before, several aspects of the data jump out immediately. First, we can see considerable year-to-year variability in the data. Not every year is warmer than the last. And second, underlying the short-term variability is a very clear upward temperature trend. On average, the globe has been warming. Later, we'll talk more about the different mechanisms that produce year-to-year variability and long-term trends. For now, suffice it to say that this short-term noise in the temperature signal arises from the different ways in which Earth redistributes energy within the system. Ocean currents, atmospheric circulation, and most importantly, the exchange of energy between the atmosphere and oceans. One well-known example of this is the El Niño cycle in the tropical Pacific. Some years, this part of the ocean is very warm on the surface, dumping energy into the atmosphere, as depicted here. Other years, it's colder, absorbing energy from the atmosphere. Now, there are many such cycles in the Earth system, giving rise to the year-to-year ups and downs in global temperature. In order to more clearly extract the underlying trend, climate scientists take longer-term running averages of 5 years, a decade, or even several decades. Here, each point on the black line is the average of the preceding 30 years. And doing this smooths out the short-term ripples or noise and makes the longer-term trend more apparent. So even though each year is not necessarily warmer than the last, we see very clearly that each 30-year period is warmer than the previous 30-year period, and that this warming trend, particularly over the last 50 years or so, has been very steady. Now, it's worth looking at this data in one more way to see how looking at year-to-year variability can be misleading if your goal is to understand a long-term trend. We'll plot this data as bars and look at just the last few decades. And if we take a warm year from the 90s and compare it to a cool year from the 2000s, it can seem that warming has stopped, or at least paused. Look, no warming. But of course, this is not a reliable analysis technique because we had to cherry pick our years just right to get this result. And if we change just one of our endpoints by just a single year, voila, we get a completely different result. So looking at year-to-year variability is not a good way to pick out a trend, just like watching a few waves roll into the beach won't tell you if the tide is coming in. Instead, if we look at longer-term averages, we get a clearer picture. Each decade is warmer than the last, and this is true no matter how we choose our decades. Utah Climate Notes is a collaboration between the Utah Climate Center and Cooperative Extension, making essential climate science real for the people of Utah.